questions about anything from last time? About anything? Well, last time we were studying monotone functions, and I was concentrating on the increasing case. The decreasing case would be analogous with all the inequalities reversed. And I was about to do a very exciting thing, showing that an increasing function can have at most countably many jumps. And remember what the jump business was. The picture, that's a typical increasing function there that might have a jump. And if it does have a jump, that value coming from the right is the inf of the f of x for x bigger than c. And coming from the left, that value is the sup of f of x for x less than c. Okay. If that number on the bottom is always less than or equal to the number on the top. Because everything to the right is greater or equal to everything to the left. That's why that is. And the actual value of the function at the jump could be anywhere in between those dots. I'll make those dots colored. The actual value could be anywhere between those two red dots, and it could be equal to one of those red dots. Okay, and so remember the fact from last time is that f is continuous, little f, is continuous at c if and only if that jump is 0, meaning the sup is equal to the inf. That's the fact from last time. And now I'm going to demonstrate the famous fact that I mentioned, called the theorem. A monotone function can have at most countably many jumps. On a closed interval AB, and have at most countably many, so it could be a finite number, or it could be a countably infinite number. Okay, and I started sketching out what the proof was going to look like. Let's see. The picture was, let's assume we have a, last time I said a less than or equal to x1. This time I'm going to say a less than x1, less than x2, less than etc., less than x capital N, less than b. And suppose the x's are jump points. They're not all the jump points, they're just jump points. And the last time I claimed that the sum of those the jump quantity, sum as n goes from 1 to capital N of the jump amount, that has to be less than or equal to f of b minus f of a. Okay, and then the book, of course, says why. This is actually the interesting part of the theorem. I guess whenever you draw these pictures, you believe it, because the jumps are always less than they look like, at least in my pictures. They look strictly less, because my pictures are It's true that a constant function is increasing by the definition, but I would never draw that as my typical function. So if the function was, well, there would be no jumps. I guess if there were no jumps, all those jumps would be 0, and the right-hand side would be 0 too, so it would be still true. Okay, so here's the y. I'm going to draw a graph here of something more typical. Okay, let's take an xk right here where there's a jump. Okay, that means there's going to be that picture from before. And maybe the c's in here. Okay, it's increasing, so might look like that. And there might be more jumps. So there might be another jump here. There might be another jump here, etc. And let's say that the next one in my sum there is over here someplace. And my previous one is over here someplace. I don't really want that to look like it's 0. Okay, so this would be xk minus 1. And I want to figure out a way of comparing my jump amount, which is this thing right here, to actual values of the function. Well, if I pick any value over here, call it u sub, I'm going to call this one u sub k. Just pick any old thing here, u sub k. And pick any old thing here, u sub k plus 1. So pick those. So the u sub k's are just between the two of those things. So you pick those, and then you realize everything to the left of the jump is less than or equal to everything to the right of the jump. So in particular, so the definitions make it easy to see. I'll write it out. Everything left of the jump is less than or equal to everything right of the jump. So in particular, f of uk would be less than or equal to the sup of everything less than to the, okay, and we know that's less than or equal to the inf for x bigger than c, f of x. And since that's the inf, that's less than or equal to f of uk plus 1. So, hallelujah, we see that, what's the big one? The big one is f of uk plus 1. What do I want to write? Yeah, the jump is smaller than, I want to bound the jump. So the jump at xk, that's equal to the inf minus the sup. And we see that that's less than or equal to f of uk plus 1 minus f of uk. And now the key is, so the sum of the xk, jxk's, as k goes from 1 to n now, is going to be less than or equal to the sum of these actual values. And those telescope. So let's see, those would telescope down to f of u, what did I say, k plus 1. Yeah, the k plus, the last one would be the one I'd have to stick between one. So the last one is between, let's see, that was my last xn, and this thing would have to be less than un plus 1 less than b. And this first one would be a less than u1 less than x1. And since, what do I have? I'd have f of a is less than or equal to f of u1. I'm probably going overboard on this. Is less than or equal to un is less than or equal to f of b because it's increasing. So check. Sum of the jumps is less than or equal to f of, this is un plus 1. Okay, I might have gone overboard on that because it's basically a picture proof once you get down to it. But those are the gritty details. Questions about that? And now for the fun part. This is all I need to see that the number of jumps can be, there's only finitely, countably many. Let's see how to use this. Well, let's see. The jumps, ask yourself how many jumps could there be that are of a certain size? How many jumps can be greater than 1, let's say? Or how about greater than 1 over n? Where n is a positive integer. Well, let's think about that. Let's have the number of those jumps. Oh, let's see. Oh no, what's happening? Let's say x1, let's make them order them so I have a less than x1 less than blah 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 less than xn less than b. Have jumps. Greater than jk greater than 1 over n. Okay, then I would have n times 1 over n. See, the sum of the jn's. Let's see. each one of them is bigger than 1 over n, and there's n of them. So that would be greater than n times 1 over n. And we know that that thing on the left is less than or equal to f of b over, so we get 1 over n times capital N is strictly less than f of b minus f of a. And so the number n has to be less than n times that. So I couldn't have more, let's see. Here's where the Archimedes principle comes in. N eventually gets bigger than that. I mean, and so that shows that the number of jumps of size bigger than 1 over n has to be less than some number. And that's the number. That would be the first integer bigger than that thing, would be the number that's forbidden. So what we see here is that there's only finitely many possible. The number of points with jump size greater than 1 over n must be finite. Okay, so if something has a jump, that jump is a number, it must be bigger than some 1 over n. That's the Archimedes principle again. I guess that's the first place I use the Archimedes principle. So let's see, the set of all jump points that would be the union, as n goes from 1 to infinity, of the set of all points where the jump value is greater than 1 over n. And it's an easy fact that the countable union of finite sets is either finite or countably infinite. It's an easy fact. A countable union of finite sets is countable. Okay. If there's only finitely many, then of course that's the easy case. But if there was infinitely many, then you get an infinite union of those things. And how would you, let's see, how would I demonstrate that that's countable? I'd take the first one in the union there and set it here. It's finitely many things. Okay. And then the next one, the next set, I'd look at, it's also finite, but maybe some of those terms appeared in the first one. I would toss those out. And then I'd put those here. The next one's also finite, but maybe some of those have already occurred. I toss those out. And I put the new ones here. Okay, and I keep doing that. And after I do that, then the countability is obvious. You do it how you count. You go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, etc. You get a map to the integers that way. And since it's infinite, you get all the integers that way. And you see that I hit everything. So I get a one-to-one onto map counting those to the integers. So it's exactly how you would count it with your finger. Or if somebody gave you a pile of junk to sort out and do that with. Count pennies or something. I'll erase this. Questions about that? I think that's pretty nifty. Typical, you sit around and think about something for a long time and it hits you what you have to do. Well, we're actually moving on to a new chapter now, and it should feel a lot like freshman calculus. We're moving on to chapter 6 about differentiation. But before I did that, I thought I'd mention a couple things that I skipped. So before I move on, which is about differentiation, I thought I'd mention some fun things that were mentioned in the previous section about approximation. So I can approximate continuous functions by step functions. It's kind of an application of uniform continuity. So we can approximate continuous functions on a closed interval, B, by step functions. That turns out to be an important thing to do when you study integration, because remember when you saw Riemann sums, they were areas under step functions. And so it's going to turn out that this fact is useful to us at some point. So it's an easy thing to see basically by a picture proof. So let's let epsilon be bigger than 0 and f be continuous on a closed interval AB. Then one of the big things from the last week was we know that f is uniformly continuous there. On a closed interval, at least. And this is where uniform continuity gets to be really important. So there's a delta such that x1 minus x2 less than delta would yield that f of x1 minus f of x2 is less than our epsilon. Okay. And now, if you think about now partitioning the AB interval into little segments that are less than length delta. So here's the, I want to cut up the interval AB into segments of size less than delta. Okay, so if you think about your freshman calculus, I need a delta x that's less than, let's see, delta x would be equal to b minus a divided by the number of segments in the partition. So I need b minus a over n to be less than epsilon. No, delta. And it's Archimedes principle again. I can find such an n. Pick an n natural number that does this. Then the construction of a step function is a snap. I'll just draw the picture rather than write out the details. Let's see, I'd have an A here and a B here, and I partition the interval here like that. Let's see, these would be xk's. This would be, what don't I have? This would be, A would be x naught. This is x1, x2, and B would be x sub n. Dot, dot, dot. And let's see, what are I'd have a formula for those xn's. X sub n is equal to A plus n times my delta x. And now if I was going to give you a step function, let's say my function is continuous and looks like this. I could make step functions by picking values inside those intervals. And sort of the obvious thing to do is to pick the left endpoint. I'm going to erase some of these so you can do the dot, dot, dot business, etc. Okay, I like to do the left endpoint. I could make it be the right endpoint. It doesn't really matter. But all those things are size less than delta. So the x1 and x2s inside those little purple, in each size of little interval, would be less than delta, and so the values would be within epsilon of each other. And so this step function, using uniform continuity, would be within epsilon of the blue graph, or the purple graph function is within epsilon, a tolerance of epsilon, of f of x, the graph of f of x. And so you can say that I've approximated f of x within epsilon by a step function. So that's how you do it. And there's lots of ways of doing it. I could have picked the right endpoints. I could have picked a point in the middle. I could have taken the nth on the interval or the soup. However I do it, it would just pop out in a snap. Questions about that? That's going to be useful later on when we do Riemann sums for integrals. There's a famous theorem that we're not, maybe I'll do it later. It seems it's a theorem that belongs in this course, and it's one of those beautiful famous theorems that Weierstrass thought of. It's called the Weierstrass approximation theorem. And it says this: given a continuous function on a closed interval, on closed interval AB, and the epsilon bigger than 0, there is a polynomial that's the key word, P of x, might have high degree, you never know how high the degree might need to be, but that polynomial is within epsilon of f on the whole interval. So f of x minus the polynomial less than epsilon for all x in the interval. And so the fancy math language for saying that is that I can uniformly approximate f by polynomials. To any degree of accuracy I want. Well, there's lots of proofs of Weierstrass's theorem, and they're all kind of fun and interesting. The simplest ones use integration, so that's why we're going to save it for later. So we can uniformly approximate continuous functions on a closed interval by polynomials. A fancier math word for saying that, polynomials are dense. If you think about the distance between two functions as being that epsilon distance in the graph, then this means that the polynomials are close to anything you want. They're dense. And we'll make a mathematical meaning out of that word at some point. In fact, we have the density of the rational numbers in the real numbers. It's a very similar idea. But then a great advance in math is you start thinking of functions like points, points in a space, and the distance between two functions as being like the epsilon in the picture. And when you think like that, you can use the same words to describe fancier things. That's kind of a theme in math. They're dense among continuous functions. On a closed interval. I guess I'm tying up loose ends before I move on to differentiation. 6.1 will be easy for you to read because it's going to feel like freshman calculus. So I'm going to encourage you to read it carefully, and I'll get to the main points soon. Let's see, the last thing I wanted to do before we move on is this famous thing. I guess it's not really famous. I would call it a continuous inverse function theorem. Is that what the book calls it that? A continuous inverse function theorem for monotone functions. That's what I'd call it if I had to call it something. And rather than give you proofs like I've been doing today, I'm going to give you a picture proof of it. Let's suppose I'll do the increasing version. There's a similar theorem for decreasing. Let's suppose f from AB into the real numbers is an increasing and here's it, we need it to be continuous. Let's see, yeah. Then f is maps, we know, let's see, I'm going to, rather than, we know f, I'm going to prove this theorem as I state it. We know f maps AB to an interval. That was the interval theorem. Oh, let's see. Doggone it. I want f to be a strictly increasing function. You would very quickly say that this thing can't possibly be true if you thought about a constant function. So a key word here is strictly. I should put that in the title, but the book didn't. Suppose it's a strictly increasing continuous function on AB. We know that f maps AB to an interval capital A, capital B, which is also a closed interval. The fact that f is strictly increasing so that's the picture. Okay. And the intermediate value theorem means we know that everything gets hit. I guess that's a remark. Value theme means that the whole interval gets hit. Okay, now I'm going to start drawing pictures. Here's my A, here's my B. F is increasing and it's continuous, so there's no jumps. Oh, it could be concave up or concave down, but it's increasing. Okay. The value of f at little a is big A. And the value at little b is big B. Okay, I just showed you that that map is onto because of the intermediate value theorem. So f maps AB to capital AB. It's onto by the intermediate value theorem. Okay, and it's one-to-one because it's strictly increasing. So 1 to 1 because it is strictly increasing. Let's see, why is that? We'd have, let's say we have f of x1 equals y and f of x2 equals y. And then you just, I'll pick I have two things that equal y. And I can assume that I can make the x1 be the lesser if x1 is unequal to x2. Choose so that x1 is the smaller. And then, oops, strict increasing means that can't possibly happen. And so that would be a contradiction. So this is a remark. Okay, so it's 1 to 1 and on to. And so the inverse function exists. G from AB to little ab exists. And of course, it's 1 to 1 on to too. And so here's some easy things. G is also increasing. Just from the definitions, that's an easy thing to check out. Easy to see. G is also strictly increasing. Just from the definitions and turning it all backwards. Okay, and now it's another easy thing to see is that G cannot have jumps. So one thing is it's strictly increasing, and the second thing is that G cannot have jumps. Because jumps are spots that get missed. Because points and jumps get missed. And G being 1 to 1 and on to can't miss anything. Okay. So let me go back to my graph and look at it for a second. If I have, how would I prove some of these things? I have an x1 here and an x2 here. And I guess if I start with a y1 here, there'd only be one x1 that could have that. I missed it. Here's where the y1 should have been. If I started with the y1, I could find you with exactly one x1 in this picture. And if I started with a y2 here, that would determine exactly one x2 here. And playing around with these x1s and x2s, I would show you that the g function is 1 to 1 and on to. Here's the y1. A. And I wish I had, I was going to bring a transparency. Because if this is f of x, y equals f of x, how would I get a graph of x equals g of y? Okay, here's how I do it. I put my transparency on the screen. You can do this with an overhead projector or a document cam. All right. This is the x-axis and this is the y-axis. Okay. Then I pick it up and I flip it upside down, and I move the x-axis to vertical and the y-axis to horizontal. Have you ever done that? You get the graph of the inverse function that way. All right, so here's my thing. I grab my x arrow and my y arrow, and I flip the paper over and put the x up here and the y down here. And that spits out the inverse. And if G had jumps, okay, so here's what I just told you what I would do there. I'm going to blow the whole hour on this. I take that transparency, I flip it over and stick the x-axis pointing up and the y-axis pointing that way. And then the graph I would see here, what would it look like? I think it would look like this. What would it look like? Yeah, it would look like that. This would be A, and this would be B. This would be little a, this would be little b. And if G had jumps, I'd miss something between A and B. And I can't miss anything between A and B. So this would be a graph of x equals G of y. And that thing can't have jumps, because if it did, it'd miss. Can't have jumps. Because it can't miss any segments. Okay, and we know that monotone functions that don't have any jumps are continuous. And that's the big deal here. We see that the inverse function has to be continuous. So the big deal is that continuous monotone functions have continuous inverses. That's the last line in the theorem. Monotone functions have continuous monotone inverses. Okay, what's a famous picture to finish off with today? E to the x is monotone increasing. It's 1 here, and it increases fast. And if I make a dotted line of y equals x, let's see, y equals x.